Hey there, and welcome to video 7.1. We're going to be talking about gas laws, the behavior and mathematical descriptions of an ideal gas. So when we're talking about a gas, we have to think about what physical things affect that amount of gas. And we talk about four different things when we're doing that. First of all, we talk about the pressure of the gas. How much pressure is pushing down on that gas. We also talk about the volume. How much space is that gas taking up? What is the temperature of the gas? And how many moles of gas are there? How many particles are actually present? So those four variables are going to allow us to quantify that particular sample of gas. The first thing we can talk about is the pressure. Pressure is a force per given area. The pressure itself is due to the gas particles colliding against surfaces. So if a gas particle hits a wall and bounces back off, it has given a pressure, a force, in that given area. So the whole idea of gas pressure is due to the collisions of gas particles against other surfaces. How do we measure it? Well, I know my car tires are in pounds per square inch. So pounds of pressure per square inches of area. We will also be talking about millimeters of mercury, a unit called atmospheres, and the metric unit of pascals. There are different ways we can talk about pressure, so the qualities we need to be aware of are 760 millimeters of mercury is the same as 1 atmosphere of pressure, which is the same as 101.3 kilopascals. Pascals are newtons per square meter. So we're doing kilopascals, thousands of pascals. Volume is obviously just the amount of space taken up by that particular gas. Usually we do it with displacement of water, where we bubble the gas up through a tube, displacing the water in the tube. So as the gas accumulates, it pushes the water level down, and then we can read the volume on a graduated system. Units we talk about usually are milliliters, which are the same as cubic centimeters, and also liters, which we know are the same as cubic decimeters. In terms of temperature, we have discussed before that temperature is a measure of the average kinetic energy of the particles, how fast they're going, and their relative size. Temperature is proportional to kinetic energy when we discuss the temperature units in Kelvin. So perhaps you've heard of Kelvin temperature. Kelvin temperature is defined as 273 plus the degrees Celsius. Kelvin does not have a degrees sign with it. It's just Kelvin. So 273 plus your Celsius temperature gives you Kelvin. Now, when do we have to use this Kelvin? Always. We always have to do Kelvin temperature when we're dealing with gas laws. The other variable, N, the amount of gas, is just the number of moles. So how many moles of gas are present? That's your N value. So let's talk about relationship between variables for a gas. The pressure of a gas is inversely proportional to its volume. In other words, the higher the pressure on the gas, the smaller that gas becomes. The volume drops. So if pressure goes up, volume goes down. If pressure goes down, volume goes up. Get the idea? So pressure is proportional to 1 over the volume, or we could say that the pressure times the volume is a constant. The pressure goes up by 5, the volume becomes 1/5. If the pressure goes up by 8, the volume becomes 1/8. The pressure times volume is always going to be a constant. This here says pressure is proportional to temperature. So if I start to increase the temperature of a system, the particles are moving faster, they're bouncing around with more energy. The pressure inside that system would rise. Think about taking like a can of pork and beans and putting it on your burner without opening it. What's going to happen? Temperature will increase. The pressure also increases until it explodes. Do not make that a lab assignment. In other words, pressure divided by temperature also has to be a constant. So if the temperature increases by 5, the pressure would increase by 5. If we doubled the temperature, the pressure would double. So that always remains a constant. The last relationship just says that the pressure is proportional to the number of moles of gas that are present. So the more gas I have inside a system, the greater the pressure is going to be. Why? There's more particles bouncing around. They're hitting the surface more often, therefore the pressure would go up. So if pressure is proportional to the number of moles, then if I double the number of moles, the pressure would double. If I triple the number of moles, the pressure would triple. The P divided by N would also be a constant. Now, because my pressure times volume is a constant, my pressure divided by temperature is a constant, and my pressure divided by the number of moles is a constant, then we can arrive at the fact that P times V divided by N times T would also have to be a constant. So I'm just combining these formulas into one equation. P times V, P divided by T, P divided by N, that becomes PV over NT. Now, this constant that we talk about when we take the pressure times the volume divided by the quantity number of moles times temperature in Kelvin is what we call R. R is a very special constant. It is the pressure times volume divided by number of moles times temperature, and we get a specific number, a constant. It does not change. R is called the ideal gas constant. This number pops up in chemistry, it pops up in physics. Anytime we're dealing with gases, the ideal gas constant is around. Rearranging our formula of PV over NT equals R gives us what we call the ideal gas law. The ideal gas law, pressure times volume equals number of moles times our R value times our temperature. So what is this R value? It depends on what pressure units we're using to measure that particular gas. If we're dealing with atmospheres of pressure, then our R value is equal to 0.0821 atmosphere liters per mole Kelvin. Yes, it has 4 units because if we look back here, it is actually made of 4 different variables. If we're dealing with kilopascals of pressure, then our R value is 8.31. If our pressure measurements are in millimeters of mercury, it is 62.4 millimeters of mercury liters per mole Kelvin. So what does all this mean? It means that if I know 3 of the variables, I can find the 4th. If you tell me the pressure, volume, and temperature, I can tell you how many moles of gas are in there. If you tell me how many moles of gas, the volume, and temperature, I'll tell you the pressure of that system. If you tell me the pressure, number of moles, and volume, I can tell you the temperature of the system. Given 3, I can find the 4th. So let's take a look at this problem. 12.50 grams of carbon dioxide is introduced to an evacuated 6.00 liter container at 25 degrees Celsius. Find the pressure in atmospheres in the container. So the first thing we're going to do is get the moles of gas because there is no room for grams in the equation. So if I have 12.50 grams of carbon dioxide, the molar mass of carbon dioxide is 44 grams per mole, I get 0.284 moles of carbon dioxide. That is my N value, number of moles. I also have a volume, I also have a temperature, and I'm looking for pressure. PV equals nRT. So to solve for pressure, we're going to move the volume underneath, and we arrive at pressure equals the number of moles times R times temperature. So how many moles do we have? 0.284 moles. What is my R value? In this case, we're looking for the R value that has atmospheres. Our R value that has atmospheres is the 0.0821. So that 0.0821 atmosphere liters per mole Kelvin. Yes, we have to account for all 4 of R's units. My T, temperature, 25. And hopefully you're screaming right now saying, no, 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 we have to use Kelvin. So if I take my 273 plus my 25 degrees Celsius, I get 298 Kelvin. That's what has to go in there. And we're dividing by our volume, which is given as 6.00 liters. Now, our moles are going to cancel. Our kelvins are going to cancel. Our liters cancel. What are we left with? Atmospheres. So now I just pull my calculator out. 0.284 times 0.0821 times 298 divided by 6. This gives me 1.16 atmospheres of pressure. So given 3, I can find the fourth. Doesn't really matter which particular variables I'm talking about. I could be given any 3 and I can find the fourth because I always know R. R is always going to be one of these values, depending on the different pressure units. If I'm talking about atmospheres, I use 0.0821. If I'm talking about kilopascals, I use 8.31. If the pressure is given in millimeters of mercury, I'm looking at 62.4. The second law we want to talk about is called the combined gas law. Now, we established that pressure times volume divided by the number of moles times temperature is a constant, R. Well, R has to equal R. Therefore, P times V over N times T in the initial condition has to equal P times V divided by N times T in the final condition. Why? Because they have to equal each other because they are both R. This particular equation is going to allow us to look at how changes in one variable affect the other variable, or changes in multiple variables affect another variable. In other words, if I have a balloon that has a certain pressure, volume, and temperature, what happens if I let it go and the pressure and temperature change? How does it change its volume to allow for that? So the combined gas law is going to allow us to look at how a change in a variable affects the other variables. So let's take a look at this. In a certain experiment, a sample of helium in a vacuum system was compressed at 25 degrees Celsius from a volume of 400 milliliters to a volume of 93.2 milliliters, where its pressure was found to be 200 millimeters of mercury, and the pressure was 60 degrees Celsius. What was the original pressure of the helium? So what we're going to start with is our statement of the combined gas law. PV over NT equals PV over NT for the final condition. So this is my initial condition, here's my final condition. The first thing we can do is really look at what variables are not changing. Because if I have a constant on both sides, I could certainly eliminate it from the expression. So here's my temperature, I have volumes, I have temperatures. It doesn't look like the number of moles of gas is changing. I haven't added or removed gas in this. In other words, I can get rid of my N from this expression. I end up with PV over T equals PV over T. I'm looking for the original pressure of the system. So when I want to isolate a variable, I simply move the other variables to the other side. Unless that variable is in the denominator, then I would move it first to the other side. We end up with initial pressure equaling final pressure times final volume times initial temperature divided by initial volume times final temperature. Now it's just plug and play. So my PI equals final pressure times final volume. And of note, I can use milliliters in the combined gas law. In the ideal gas law, PV equals nRT, your volume has to be converted to liters. That's not the case here. Initial temperature, 298 Kelvin, divided by my initial volume times my final temperature. So it looks like 60 degrees, so 273 plus 60 And I get 41.7. What units? Well, my milliliters are canceling, my kelvins are canceling, so this is millimeters of mercury remaining. Our third law is called Graham's law, and it deals with how fast particles can undergo diffusion or effusion. Diffusion is simply the spreading out of these molecules, or atoms, once the partition is removed. How quickly do they spread out to create a chaotic system where they're all kind of the same? Effusion is its ability to escape through that little hole, which would obviously be a function of how fast they are moving. They spread out until they're kind of even throughout the system. So let me explain to you how this whole thing works. Perhaps you're familiar with kinetic energy. Kinetic energy, to anybody in physics, is 1/2 mv squared, where m is mass and v is velocity. We already said that Graham's law is really about how fast particles are moving. So if I have two gases at equal temperature, they must have the same kinetic energy. Well, we know kinetic energy is the mass, 1/2 mass times velocity squared. So I'm going to call one side mass 1, velocity 1, the other mass 2, velocity 2. Now to solve this, I could multiply both sides by 2, and the half would go away. I could divide both sides by m2, and then by v1 squared, and then take the square root of both sides, and I'll arrive at Graham's law. So Graham's law says velocity of particle 2 divided by velocity of particle 1 is equal to the square root of mass of 1 divided by mass of 2. So what this is going to allow us to do is compare the velocities, the relative velocities of two different particles, given that they might have different masses. Now the secret to this is understanding that heavy particles are going to move slow relative to smaller particles that have to move fast in order for them to have the same kinetic energy. So if I had two bottles, brilliantly drawn bottles, of substance A and B, and I were to uncork those both, which particles would spread across the room faster? Which one would diffuse faster? Well, the smaller ones are going to end up moving a lot faster than the heavier ones. Why? Because they have the same kinetic energy. Kinetic energy deals with mass and velocity. So the heavier ones are going to move slow. The lighter ones, relative to it, are going to be fast. The smaller you are, the faster you move. So which gas has a higher rate of diffusion? Helium gas or carbon dioxide gas? Well, let's answer that first question. If I look at the periodic table, helium has a mass of 4.0 grams per mole. Carbon dioxide is at 44 grams per mole. So clearly, the carbon dioxide is heavier, the helium is lighter, so the helium must be faster. How much faster? So what we're going to do is use Graham's law to quantify this. I'm not going to worry about velocity rate calculations. I'm going to use my noodle right now. I know that helium is faster. If I can take a look just at this part of Graham's law, I'm going to take the big mass divided by the small mass, and then take the square root of that quantity. So the square root of 11 is 3.32. That tells me that helium is 3.32 times faster. So now when I look at this equation, helium is at 425 meters per second. That must mean carbon dioxide is less than that. So am I going to multiply the 3.32 by the velocity or divide to get the correct answer? Well, if I need something smaller, obviously I'm going to divide. So I'm going to take my 425 meters per second divided by my multiplier I found by taking the square root of the larger one by the smaller one, and I get 128 meters per second. Well, that seems to make sense because we know carbon dioxide has to be slower than the helium. How much slower? 3.32 times slower. So take the larger mass divided by the smaller mass, take the square root, you get a multiplier that's going to tell you how much faster or slower one gas is than the other. Then we're going to decide whether to multiply or divide based on how the problem looks. Our last law, Dalton's law of partial pressures, says the total pressure of a system is equal to the sum of the partial pressures of its constituents. Doesn't that make sense? If all the gases are added up together, that's the total pressure. Yeah, total pressure, he taught, total pressure is equal to one pressure plus the other, etc. So air itself is made out of oxygen, nitrogen, argon, water, carbon dioxide. 78.1% of it is due to, 78.1 kilopascals of pressure are due to nitrogen. 20.9 kilopascals are due to oxygen. 0.97 kilopascals are due to the argon. 1.28 kilopascals are due to water. And 0.05 are due to the carbon dioxide. When I add these all up, I get the pressure of the air. Simple law. The law I like to use a lot is that the pressure of gas 1, is equal to its mole fraction times the total pressure. So P1 is the pressure of that gas I'm considering. X1 is the mole fraction of the substance, and the total pressure is the pressure of the system. The mole fraction is simply moles of the thing you're looking for divided by the total number of moles. So it tells you how many moles of what you're considering divided by the total number of moles to tell you what fraction of the pressure is due to that particular gas. So if 12 grams of oxygen and 1.8 grams of hydrogen are placed in a container to produce a pressure of 923 millimeters of mercury, what is the partial pressure of the hydrogen? So my first step here is to figure out how many moles of oxygen and hydrogen are present. I have 0.38 moles of the oxygen. I have 0.9 moles of the hydrogen. So my pressure of hydrogen equals the mole fraction of hydrogen times the total pressure. My mole fraction is equal to moles of the hydrogen divided by total moles. So 0.90 divided by the quantity 0.38 times 0.90. Then I'm going to multiply that by the total pressure, which is 923. So my pressure of hydrogen is 98.0 millimeters of mercury. And be careful that make sure that those total moles in the denominator are in parentheses, and you do that on your calculator. So what's so damn ideal about it all? Well, an ideal gas is defined as one in which the collisions between atoms and molecules are perfectly elastic. They bounce off each other without a loss of energy. There are no intermolecular attractive forces, so when they slide by one another, those dipole and dispersion forces aren't affecting their velocity. The particles have no interaction. We also assume that the volume of the particles themselves is zero. They don't occupy any of their own volume, which is a great assumption because if we look at the distance between molecules or atoms in a gas, they are very far apart relative to how big they are. It's a pretty darn good assumption for all small molar mass gases at normal temperatures and pressures. We don't see much deviation. So we can treat carbon dioxide the same way we treat helium, the same way we treat oxygen, the same way we treat sulfur dioxide. We still just treat those as ideal gases under normal temperatures and pressures. So we have 4 laws we have to decide when we're going to need to use those. The first law, the ideal gas law, is when we are given 3, find the fourth. Again, if I know pressure, volume, and temperature, I'll tell you number of moles. Give me moles, temperature, and volume, I'll tell you the pressure. Give me pressure, volume, and temperature, I'll tell you how many moles. Something like that. Given 3, I can find the fourth. The second law we use when we have a change in the system. So if the problem gives you 2 different pressures, or 2 different temperatures, or 2 different numbers of moles of gas, then something is changing, we need to use the combined gas law. And again, we're going to eliminate variables that don't change, solve for the variable we're looking for, and then it's just plug and chug. Law number 3, Graham's law, deals with how fast particles are moving relative to one another. So if the problem is asking about how fast, what rate are they diffusing or effusing, what is the speed of particles, that is Graham's law. And again, we're going to take the mass of the large particle divided by the mass of the smaller particle, take the square root of that, and it's going to tell us how much faster the smaller particle is than the larger particle. With that, we're going to divide or multiply by that particular number to get the correct answer. And law 4 deals with pressures within a mixture of gases. The total pressure is the sum of all the individual pressures. Or we can take the mole fraction of what we're looking for times that total pressure to figure out the pressure of that individual gas. So in this unit, we're going to be exploring how do we quantify gases, how can we use the gas laws to solve for a particular variable about that gas to describe its behavior, and it's going to actually push itself right back into the stoichiometry because we already know how to use solids, we can deal with solutions, now we can deal with gases as well. We're covered. I will see you very soon. Thanks.